So finally, this lecture is about impedance and a different technique, node analysis, for solving a circuit problem. So impedance, by definition, is the ratio, okay, ratio to 3-bar ratio of the V in the S domain and the I, the current in the S domain. So for the capacitor, you have a V sub t equals 1 over C times integral of I dt, which is same as V dot equals 1 over C times I. If you take a Laplace transform, you'll have S times V in the S domain equals 1 over C times I in the S domain. So now find the ratio of a V over I, then you'll have 1 over C times S. Okay. Usually C will be given, it's a capacitance, it will be given, and S is just not a number. Okay? It's a Laplace variable. So the impedance of the capacitor is 1 over Cs. The impedance for the inductor can be obtained the same way. What you do is you start with a V equals at L di dt. Take Laplace transform, you'll have V sub S equals L times S times I sub S. Now do the same thing, find the ratio. What's V over I? Okay, V over I in S domain. That is LS. That's the impedance for the inductor. For the resistor, the impedance is just the resistance. So why is this useful? Because impedance is like resistors. Okay, if they're in series, you just add them together. If they're in parallel, you just add the inverses and invert one more time. So next one is a book example. I think I did a similar problem already, so you can practice. You can make yourself understand what these equations are. Okay. So I'm going to actually teach you a different technique. Okay, before I actually use impedance, I'm going to use a different technique of solving the same problem. Okay, so this one, if you look at the solution, it uses a loop law and the junction law, and then this is called the mesh method. And then unknown of this problem is the current. Your goal is to find the currents, I1 and I2. Okay, I1 and I2, and I3. So here, when you use what's called the node analysis, this is called the node analysis or node method. Okay, node method. Approach is a little bit different. Okay, so here we're gonna mark this point as a V out. Okay, V out. So your goal is to find the voltage across resistor number 2, R2. So now I'm gonna put a ground. Okay, put a ground here and everywhere around here. Okay, you're gonna mark the voltage to be 0 volt. Okay, 0 volt. And here, this line right here, the voltage will be V1. Okay, here, voltage will be V2. Okay, so you know all the voltage except for that point, that node between the R1, R2, and R3. So we're gonna call it V out. Okay. So now this is very useful when somebody says find the system model for the V voltage across the resistor number 2. Okay, so that's your V out. So what you're going to do is this is a node method. So what you're going to do is from that node, I'm going to redraw it right here. You have R1 and R2 and R3, and this is your V out. You're going to write a current that's flowing out. Okay, so I want you to ignore that picture right there. Why? Because I just recycled that picture from the previous problem. Okay, I don't want you to look at that one. Okay, don't mind this one. Okay, so we're going to define my I1 to be all flowing out, all the current to be flowing out. Okay, this is 3. This is your I2. Okay, flowing out of that node. And then you do know the voltage level on the other side. This is your V2, which is a source voltage. Here, the voltage level is V1. Okay, and then here, the voltage level here is the ground, 0. Okay, 0 volt, 0 volt. Okay. So how would you write the current one? I1 is Okay, current will flow to the left only if V out is at the higher potential. True. So you're going to write the V out minus V1. It doesn't mean V out is at a higher potential than V1. Okay, it's just that I1 to be defined to the left. It has to be the voltage out minus voltage 1. Okay, divided by R1. So that's going to be I1 to the left flowing out of that node. So now, same thing. We do the same thing for the I2. I2 is V out minus 0 volt. Okay, so right now I'm looking at here. I'm looking at right there. Okay, 0 volt divided by R2. And same thing. What is I3? I3 is equal to V out minus V2. Okay, so this method. So now you. The reason why we're writing the current out of that node is because it's just easier to keep tabs on it. Okay, I don't want to assume if the V1 is higher than V2 or anything. I just want to be able to I just want to write the current coming out of that node. So VO minus V2 equals to probably negative number in R3. Okay. So now what do you know about the junction law? It says that all the current going in has to be equal to all the current that's going out, okay? Or all the current, summation of all the current must be equal to 0, okay? All the current that's going out of the node must be equal to 0. So you have the following equation right here. So this is your, go on the left hand side, I already have them. So this is your I1, this is your I2, that's your I3 coming out of that node, okay? And the right hand side will be equal to 0, and we do know that some of the numbers will have to be negative for that to be 0. Some of them will be positive, some of them will be negative. So now what's the V out? You're going to solve for V out, V out, V out. Okay? So what did I do? These must be the denominator must be the coefficient of a V out, and the right hand side is a V1 divided by R1. Oh, I found it right there. V2 divided by R3, I found it right there. Okay, so this is the expression for the V out, and I usually don't like this very much. Why? Because it's a fraction instead of fraction. So I feel obligated to get rid of the fractions inside the fraction. So how do you do it? You multiply the top and bottom by the same number, which is R1 times R2 times R3, which is why did I choose that one? That's the common denominator. Okay, so after you multiply, you'll have R2 times R3 plus R1 times R3 plus, that's the new denominator. Then you have R1 times R2 in the denominator. For the numerator, you have R2 times R3 V1 of t. Okay, plus, what's the next one? It's R1 times R2 times V2 of t. Okay, that's equal to V outs of t. Okay, that's the final answer. So this node method is very useful if they're asking for what's the V out instead of the current. Okay, in fact, you don't even have to write any current, even though what you're writing here is the junction law. Okay, all the current going into the node must be equal to all the current that's coming out of the node. So compare this to the previous approach. Okay, in the previous approach, unknowns are the currents I1 and I2, and the total current I. Oh wait a minute. Yes, I1, I2, and I3, and then from solving these equations, you will be finding I1, I2, and I3. Okay. So now let's go to the next problem. So there is a reason why I showed you this, okay? Because now we're gonna do on, really, this is the same problem. It doesn't look the same, but it's the same problem. So it says, obtain the differential equation for the current I3, okay? You know, for the test, I can just change that. I can just say, I'll find the system model for the V out across the capacitor. I could do that, or the inductor, or the resistor. Okay, or I can even ask for the system model for the I1 or I2. Okay, I think I can just ask 6 different things. System, right here it asks for the current I3, but I could ask for, or find the system model for I1, I2, or the V voltage across the resistor, capacitor, and inductor. Okay, I can ask like 6 different things. So this one is only asking for 1. Okay, so let's try this. Since it's asking for the current, I'm going to continue with the mesh method. Okay, mesh analysis. So how do? Well, I need a mesh. I need a loop. So I'm going to say this is my loop number 1. Loop number 2. Oh, this is nice. Look at the current directions. They're all in the same direction. It's a loop direction, so I don't have to mess around with a negative number. So let's see. Yeah. So for the current, okay, I like to write down the easier equation first. So you have a I1 that's going into the node, okay, and what else is going to the node? I2, okay, I2 going into the node must be same as I3. Okay? This is equation 1. In mesh analysis, mesh method, your unknowns are the current. Okay, if I ask for the differential equation for the voltages, I might even use the node method, okay, or the unknowns are the voltages. So let's see. It's the mesh method. I1 plus I2 equals I3. Okay, now going to the loop 1. Loop 1. What do I have? We have a V1 gain. Why? Because I'm going from the negative to positive terminal. Okay. I don't have to give you a negative to positive in this way, right? I could reverse the polarity. In that case, you'll have to write that negative V1, right? I'm going to write that in green. Okay. If this was positive, okay, this is negative, this you have to write negative here. Okay. So let me erase this. Okay. So you have a V1 equals, now that's the gain. This is the gain. Equals, now the drop is R times I1 plus, okay, plus L times di3 over dt. Okay, so what you want to do is you actually don't want to stay in the time domain. Okay, so what you do is you take a Laplace transform of the whole circuit. Okay, think of it that way, and you're going to replace everything with impedance. So whenever you see C, you don't have C, you have 1 over CS. Whenever you have L, you have L times S. Okay, L times S. So this equation, okay, in the Laplace domain will be V1 sub S equals R times I1 sub S plus LS times I3 sub S. Okay, so this is your equation number 2. For the equation number 1, I can simply change the to I1, I2, and I3 in S domain. Okay, so this is all gonna be in the S domain. Okay. So for the loop 2, okay, for the loop 2, do the same thing. We have a V2 sub S, okay, equals, now that's equal to, treat the capacitor, treat the impedance as if it's a resistor. Okay, it's gonna be I2 sub S times 1 over CS, okay, plus LS times I3 sub S. Okay, that's your third equation. Okay, so we're trying to solve for the I3. Okay, I3, that means I want to get rid of I1 and I2. I have 3 equations, 3 unknowns, no problem. So here, since I didn't give you any numbers, I'm going to have to solve them by hand. If I gave you numbers, let me think. If I gave you numbers, I think you still have to do it by hand because of the S. Okay, S, you can't get rid of the S's. So why don't we get rid of I3? No, let's not get rid of I3. Why don't I get rid of, yeah, we can get rid of I3 because we're solving for I3. Why don't I get rid of I1? Okay, so every time I see I1, okay, I1 right here, okay, let's replace it with I3 minus I2 in this domain. Excuse me. So now let's write down equation 2. Okay, equation 2 again in terms of I2 and I3. So you have LS minus R times I2. Did you get it? I got Oopsie, that was wrong. Never mind. Never mind. Okay. Okay. So equation 2, the coefficient of I2 is negative R times I2 plus, we have LS plus R times I3. Okay, equals to V1. Okay, so I must be desperate because I dropped the whole down function of S. Okay, hold on is a function of S, V is a function of S. Okay, so that's your equation 2. Equation 3 becomes, well, it's the same thing, 1 over CS times I2 sub S plus LS times I3 sub S equals V2 sub S. Oopsie, what's that? Okay. So let me check my equation one more time. So that's R times I1 plus LS times I3 equals 2. That's it. That's your second equation. And I1 is I3 minus I2. So, yep, that looks right. Okay, that looks right. It's a little convenient if you happen to know that LS has a unit of ohms. Okay, LS is a unit of ohms. Okay. So I'll just use Cramer's rule. So I want I3. So I3 sub S equals, now the denominator will be determinant of, so you have to use absolute value sign, minus R, LS plus R, 1 over CS, LS. I just copy the coefficients. And then for the numerator, I want I3. So that means just keep the coefficient of I2 and take out the second column and replace it with a V1 and V2 sub S. Okay, so that's equal to, now I'm going to have minus R times V2 on the top. How do you find the determinant? It's going to be this multiplication now minus that one. Okay, the second one minus that one. Okay, minus the blue one. So I just, the first one, the green one, then minus, I have 1 over CS times V1 sub S. Okay, and divide by, the determinant is negative R times L times S, this multiplication, minus 1 over CS, oops, I didn't mean that, 1 over CS, okay, times LS plus R. So now you can't leave it like this, you have to simplify. So since everything is negative, can I just multiply everything by negative? Yeah, multiply the top by negative, bottom by negative, and that way it all becomes positive. So not only that, I'm going to multiply the top and bottom by CS. So you'll have RCS times V2 minus plus V1 divided by, you will have CS times RCL S squared minus plus LS plus R. Okay. That's your I3. So now, I just had enough space. So if you multiply the denominator, okay, what is this equal to? You have I3 sub S, multiply, okay? Move the denominator to the left hand side, and you have RCL S squared times I3 sub S plus LS times I3 sub S plus R times I3 sub S equals RCS V2 plus V1. So now take an inverse Laplace transform of the whole thing, and then you have RCL second derivative of I3 with respect to time. Now it's a function of time plus L times the first derivative of I3 with respect to time plus R. This is R. I'm going to write R times I3 sub t equals, let me write down V1 first, V1 sub t plus RC times the second derivative, the first derivative of the V2 with respect to time. Okay, so that's your system model. Okay, so you might say this was so painful, but it's not compared to what you have to do if you stay in the time domain. Okay, so sometimes I think I gave this problem a long time ago, and I was looking around how during the exam how people are doing. They were having, people could not solve this because why? Because they stay in the time domain from the beginning. Okay, and why don't you try it at home? Why don't you try and see, okay, how long it takes you to find the same system model? Okay, in the next example, 6.3.2, this is a book example. Look at this. I got rid of the use of black diagram representation of the circuit. Okay, let's not do that. Okay, let's not do that. Okay. Let's do the first part. It says determine the transfer function. So here it's telling you so in the previous problem we could have got the transfer function from here. We could have got the transfer function. What's the transfer function? I3 divided by V1. That would have been 1. Okay, 1 divided by the denominator. The transfer function I3 divided by V2. That would be the RCS divided by the same denominator. Okay. So here, instead of going to the time domain, it says to just find the transfer function V out over Vs. I'm going to use the node method. Okay, that's usually not my preferred method, but I'll just use a node method. Okay, why? Because they asked for the system model for the V out, which is right here. Okay, right here, V out right there. Okay, so now using the node method, you're going to indicate this is going to be my 0 line. Okay, this is going to be my 0 volt. Okay, here is V0 above 0. Right here will be just a V0. This will be your V1. So this problem is set up, they drew the picture as if you're going to do the node method. What's the voltage right there? Okay, upstream of R will just be Vs, of course. Okay, because it's a 0 volt here, and then from minus to plus you gain. Okay, so you're at a higher level at the positive terminal of the source. Okay, so that's your Vs. So using the node analysis, you have two unknown voltages. Okay, you'll have two equations. So let's start with a node where it says V1. Yeah, so you have a V1, you have a resistor R, you have a resistor R, okay, your capacitor, okay, I'm going to change the impedance. So it's going to be 1 over CS. And here you're at 0 volt level. On the left you have a Vs. Here the voltage level is unknown VO. Okay, I want you to keep in mind that you have two unknowns in the system. Which one is? The first one is a VO, and the second is a V1. And those are your unknowns. I don't want you to forget. Everything else is given. You have to consider them given. The source Vs is given. RCC, they're all given. So here in this picture, you have I1, I2, and I3 that are marked, but we're not going to use them. So with the node method, for the V1, okay, I'm going to have the following equation. I'm going to write down the current coming out of that node. Those three current. I'm not going to name them. The first one is V1 minus Vs divided by R. So that's the current coming out of to the left, plus V1 minus V out divided by R. So that's the current going to the right. And current coming down, okay, also away from the node, is V1 divided by 1 over CS. Okay, that must be equal to 0. So that's your equation 1. Remember, your unknown is V1 and V out, V0. So now next, you go to the second node, okay, VO. Okay, that node, it's a little easier because, look, okay, so this is your VO because you don't have another branch. Okay, right now this terminal right there, this is indicating you're putting a multimeter, the voltmeter, okay, to measure the voltage out right there. But the voltmeter doesn't draw any current. Okay, so there's no current going that way. So you have an R, here you have 1 over CS. Okay, so again, you're going to draw the two currents going out this way. Okay. So the first current is a VO. Okay, I forgot to write down. What's the voltage level here? On the other side of R, it's marked as a V1. Remember, they're all unknowns. If you don't know that one, you don't know that one. Okay. And then here you have a 0 volt. Okay, 0 volt. So you have a V0 minus V1 divided by R plus. Okay, plus. You have a V0 minus 0 volt divided by 1 over CS equals 0. That's your second equation. So when you look at this, these are your unknowns. Okay, unknowns. Oh, I forgot to mark the V1 here. Okay, here we go. Okay, so those are unknowns. So what's the best way to solve? Okay, solve the V0 and the V1. Okay, so like I said, I don't like to use this method because why? Because I don't like fractions. I don't like fraction inside the fraction. Okay, let me just move this one over this way. Okay, so I'm planning. Let me pause. Okay, while I was pausing the video, I just realized something. Okay, for the first equation one, there's another expression. I can do V1 minus Vs divided by R plus. Okay, so that's the current to the left. Okay, current to the left. And for this one, instead of stopping at V0, I can go all the way to C. Okay, 1 over CS. Okay, to 0 volt. Okay, so this will become V1 divided by, now you have a resistor and capacitor in series. Okay, so that means you just add them together, R plus 1 over CS. Okay, plus you have a V1 divided by 1 over CS equals to 0. Okay, so I'm going to call it equation 1 prime. The reason why this equation is better than equation 1 is because I don't have to, there's only one unknown. Okay, there's only one unknown in here. Okay, so now what you do is you're going to do some algebra. So then let me just move this out of the way. Yeah, let me move this out. I want to just move this out of the way so that way I can do more algebra underneath. Ooh, I'm a little scared. So you have a V1 as a coefficient of 1 over R plus 1 over R plus 1 over CS. I'm crying. 1 over CS. Okay, equals, now I'm going to move the terms that doesn't have a V1, which is Vs right there. Vs divided by R. Okay? Oh boy. Can I, let me see. Let me simplify. This is 1 over R plus, can I multiply by CS? So I have RCS plus 1. I have a CS on top. Is that right? I multiply the top and bottom by CS. Yes. Plus, this is just a CS. Okay? Equals to VS over R. So now, what do? I have a common denominator, which is R times RCS plus 1. Ooh, God, I knew it was going to be ugly. No wonder I never used this method. Okay, plus RCS plus, oh my goodness gracious. Okay, so this is going to be RCS times RCS plus 1. I'm not even sure if I did this one right or not. VS over R. Let me check one more time. Okay. Yes. Yes. And the third one is yes. Okay. So now let me simplify one more. V1. Oh. I want to cry. RC square S square plus RCS, 3 of them. 3 RCS plus 1 R times RCS plus 1 equals VS over R. I'm gonna cry. V1 finally is VS divided by R times RCS plus 1, R cancels. You have R squared C squared S squared plus 3 RCS plus 1. I'm gonna cry. That gives you V1 over Vs equals RCS plus 1. R squared C squared S squared plus 3RCS plus 1. Ooh, I'm really gonna cry. So that, is that what they asked for? Let me see. No, it wasn't. It asked for the V0. Okay? Don't despair. Okay? So I'm gonna shrink these. See, I didn't mean that. Stop. Okay. So, okay, let's look at the second equation, and finally, okay, finally we can find your V out. Okay, so this is no joke either, because your V out, okay, is 1 over R V out times 1 over R plus CS, okay, equals, as if extracted this term and this term, okay, and move the V1 over, so you have a V1 divided by R. So you have a V out equals V1 times 1 over R times, let me see, if you combine those two together, common denominator is R, you have R over 1 plus RCS, okay, R cancels. So what does it tell you? So V0 is equal to V1, okay, we already found what V1 is, and divide by 1 plus RCS, okay. So I see it now, what's V out divided by Vs, that's equal to V1 divided by Vs times 1 over 1 plus RCS, isn't it? Okay, and then this one is already known, okay, where? Right here, okay, right here, okay. So now you're going to take that term over, okay, and then, oh, numerator cancels, so that's equal to 1 over R squared, C squared, S squared, plus 3RCS plus 1. Okay, that's going to be your final answer right there, okay. Can I just take this out? Okay. So let's continue with the last example. Okay, you can do the rest of the homework. So let's see, it says find the transfer function between the input voltage and output. Oh, they want the V out. They want the system model for V out. Okay. Oh, look at this. This is actually quite easy. So now I'm going to use the node method, node analysis. I'm not even going to bother with the current. So this is your V out right there. Okay, right there. And then this is all 0 volt line. Okay. What's the voltage here? It's going to be Vs. Okay. It's on the positive side of the source voltage. Okay. So negative terminal, I just had to make them 0. So the node method says, what does it say? From this node, okay, from this node. Yeah. So right now this is a 0 volt, right now this is a V0, this is a Vs. Okay, Vs is a known number, okay, it's a known, you decide, okay, R1, is that R1? Okay, R and C, okay, so I'm going to use impedance. So that means impedance of C is 1 over Cs. Scratch that out. You have 1 over Cs. So since they're parallel to each other, okay, the two impedances that are parallel to each other, you can group them together. What's equivalent resistance or equivalent impedance? You can use product over sum. Okay, the product over sum. Oof. Okay, I have to simplify this again, which is, let me see, multiply top and bottom by CS. So you'll have RCS plus 1. Here it is. Okay, so this is your equivalent impedance, okay, for this just two elements. So now you have a V out, okay, V out minus Vs. Okay, what is this? It's the voltage difference between these 2 points. Okay, divided by R1 gives you the current that's going out of that node to the left. Okay, plus now you're going to do the same thing, V out minus 0 volt divided by the impedance, okay, your C equivalent. I was a little scared to write all that stuff. Oh, it's not so bad actually. That's equal to 0. Yeah, that's equal to 0. So what am I solving for? V out, right? V out. So you have a V out 1 over R1 plus 1 over C, okay? C equivalent equals Vs divided by R1, and what they want is VO, the transfer function V out divided by Vs. Okay, so this is your transfer function equals 1 over R1 divided by 1 over R1 plus 1 over C equivalent. Okay, so the rest of them is algebra. So this is, let me see, R1 cancels. You'll have 1 over 1 plus R1 divided by C equivalent. Okay, that is 1 divided by 1 plus R1 divided by C equivalent. So let me see, divide by R, and you have a RCS plus 1 on top. Okay, that's equal to, I'm going to multiply top and bottom by R, so you have R divided by R plus R1 times RCS plus 1, or that's R divided by R plus R1 plus R1 CS. Okay, so this is your answer right there. Okay, this is the end of section 6.3. Okay, 6.3.